Alright, so, person pushing it down 500 at a 45-degree angle, tension up to the right. Here's how your force diagram is going to look.
Hi, Wizard of Oz people.
I hate you, Joel.
What's that black marking up on the white thing? Left?
Right here?
Yeah.
Yeah, that was when I was doing projectile motion with AP, and I was doing this problem involving like a catapult off of a castle, and I didn't have enough room, so I just kept drawing the marker on the wall, figuring, oh, drywall marker will erase off walls. No. Doesn't erase. All right, so force diagram. As usual, we're gonna have force of gravity straight down.
Oh, we are having a seizure.
Yeah, I'm having a seizure right now. Thanks. Thanks a lot, Matt. All right, we've got tension up and to the right. This is going to be our force of tension. We've got friction to the left. And we've got a normal force straight up because we're on the ground, right? Okay, and then what's our last force?
Down to the right.
You're pushing it in what direction?
Down to the right.
Down and to the right.
That's force applied, correct?
Yeah, I drew that right, so that's a good start.
And that is an applied force. So, we just did step 2. We haven't done step 1 yet. Are we at equilibrium?
Yes. Yeah.
Yes, in fact, we are. How do we know that?
Because it's given to us in the problem.
Because we're not moving,
Yeah.
which is how it's given to you. Well, that and I said we're working on equilibrium. Shut up. All right. We also know, well, we know a couple things. We'll come back. Yeah, isn't it, Tom? All right. Okay, so step 1, we're at equilibrium. Step 2, we drew our force diagram. What's step 3?
Equation.
We write out our well, no. Even before we write out the equations, what's step 3?
Do the trick.
We do the trig. So I'm going to go back to this other picture. Do we have forces that act in more than one direction?
Yeah.
Absolutely. Which one?
The two is
So we have 2 in this problem, which is why this is as complicated as I can possibly make it. We have an attention force that's in 2 directions, and we have an applied force that's in 2 directions. Okay? So we've got the applied here over on the left, and we have the tension over here on the right. Which one do we want to break up first?
Tension.
No.
I heard tension first. Why not?
Yeah, boy.
So the tension force is in what 2 directions?
Up and to the right.
Up and to the right. So I'm going to draw my line up. Actually, here, I'm going to do this instead. No, that's not what I wanted to do at all. Force diagram? Sure.
Are you learning to
You sound like a oh wait, that didn't work, isn't it? Crap.
You know they hear you, correct?
seizure?
Who's what? It's pushed to the down and to the right and pulled up and to the right by the tension. So there's a tension and applied. I'm throwing as much as I can at him just to see him squirm.
Just to see. Well, we're not breaking today.
You always break. Not a problem. All right. So this one's up to the right, so I'll draw my components in green. We have a component up, and we have a component to the right. So we have a y component here. We have our x component here. Do we all remember how to find these?
Yeah, that's easy though.
Okay, to find x, it's opposite, so we're going to use sine. So the x component is going to equal 200 sine 30.
173.21.
That's y. Yeah, okay, I'm brilliant to that. There we go. Which is going to equal 100.
A bill.
You wish. All right. And then the x component is adjacent, so we are going to use what? Cosine.
Why don't Pythagoras do it?
That's 102 though.
You can use the Pythagorean theorem if you want. I personally, I don't like the Pythagorean theorem.
But you should know
Because
this
Pythagorean killed my father. All right.
Should you know this off the top of your head?
Oh,
though?
story time. We should just distract the Wizard of Oz kid so he gets messed with them. None of this is real.
This is a dream. This is not the YouTube video you're looking for. All right, and someone who's got a calculator because I don't remember this.
173.21.
Whoa, what?
173.21.
I should have remembered that.
Why?
Sorry, I had a seizure. Now,
wait, Mr. Bush, mess with Amy right now. Is it like just coming down to see
She'll be able to hear you, right? So when you tell her to mess with
see, John apparently has not learned that if people can only hear the recording, you might want to write said things down on like a note and hand it to someone. This kind of thinking is above John. All right, and then the next one. Pick a side. Do we want to find the Y or the X? Well, they are going to be the same because this is a 45, 45, 90 triangle, right? So let's just find one of them. Which do you like better, sine or cosine?
Oh, it's a sine.
I like
Scene, yeah. Scene A. In front of it. Scene A.
Yeah, I like 10, even though I'm too black for 10. It's not funny.
I thought it was pretty funny.
I'm doing what?
Yep.
Anyway, what's our Y component wind up being?
353.55. Look here, fellas. Mr. Bush, do not fall. Do not fall.
Shut up. Just shut up. So we've got our Y component, we've got our X. Now, someone else is going to stumble onto this, like some lawyer is going to stumble onto this on YouTube and go, oh my God, that teacher's abusing his students. I'm going to sue him. And I'm going to lose like the $10 I have. Thanks. Thanks a lot. All right. No more Mountain Dew because I'll have lost my $10. So there's the Y component right there, which in this case is also going to be our X component. All right.
Wait,
Moving on.
I have a question.
what's the force of gravity?
What?
Is the force of gravity
700. No, 7.
We're going to get there.
Right,
Hold on.
negative.
One thing at a time. Okay?
Okay?
So, going back.
Hey, buddy.
I'm going to redraw my force diagram real quick. I don't care if you say no. I'm doing it anyway.
No.
So you have the force of gravity. Tell you what, let's go ahead and find that force of gravity now. If the mass is 500,
Negative 5,000.
the force of gravity must be negative 5,000. Because remember, that's the 500 times the negative 10, correct?
I did everything right. So
You don't have to redraw this
equation part.
You don't have to, no. I'm just, especially when you've got more than one vector at angles, it just tends to be easier to redraw just to clarify. Okay, we have the normal force up, which we currently have no clue what's happening with that. We have a Y component of tension. Get up. No.
You're drawing on the wall.
I am drawing on the wall. That's up, so this is Ty. And what did that equal again?
100.
The Y component was 100. And we also had a Y component of the applied force. Now, which way was that?
Down.
Down. What was its number? It was 353.53, right? 55. I'm horribly sorry. But that's down. So we have a downward component. And this is the applied force Y component.
It's on his head.
And that's negative. Alright, so we've got up and down taken care of. Now it's time for left and right. We have friction that we know nothing about so far.
Now, is that tension force of the Y the whole normal force? Is that the tension Y, is that the whole normal?
No, we don't know anything about the normal force yet.
Oh, okay.
Okay, and this isn't drawn to scale yet. I'm not worried about the scale too much.
Where
So.
did you get the TY?
That was back from our components. See, we found the component there. So that's where the Y component came from.
Oh, I remember.
Cool. All right. So there's my go-to acknowledgement of a statement. Would you prefer bite me? Come on now, people. Wow, that just happened. All right. So the force of friction is to the left. Now to the right, what do we have?
We have a force applied.
We have an X component of tension, and we have the X component of the applied force, correct?
Yeah.
Okay, so we'll put both of those. The X component of tension was 173.
Where does all this math come from?
The component.
No, that's like a rhetorical question.
You could have fooled me, Joel.
So we have the x component of tension, we have the x component of the applied force, correct?
Yes.
Okay. Now look, what are the only two forces we don't have any numbers for? Friction and normal. So, we've drawn our force diagram. We've determined we're at equilibrium. We have determined, we've broken up our vectors. What's the last step we need to do before we can figure out our answers?
Draw the equations.
Write the equations. Okay, so I'm just going to zoom in here on a patch.
This is where I got stuck at. I didn't know like you could draw another force diagram.
You don't have to, but it helps kind of clarify what's going on. In the x direction, we have the x component of the applied force plus the x component of tension plus friction. And that's all going to add up to, because we are at equilibrium.
Well, we're not at equilibrium. All we got
Oh, whoa, 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 whoa. That's Friday.
We just take 0 to whatever number is.
That's Friday. Back the moving ahead truck up.
Ooh. Yeah.
All right. In the y direction, what do we have?
Force AY. Force applied.
We have the y component of both applied and tension, right? Plus what? Plus gravity and... Holy crap! There's 4 forces. We can't possibly do this. Except we know the force tension y component. We know the force applied y component. We know the force of gravity. We know the x component of the applied force. We know the x component of tension. Hey, it looks like the only 2 numbers we don't know are the only 2 forces we don't know. Can we now figure those out?
Yeah, we add them and then
We add them up. So for example, in the x direction we're going to have, let's see, like 353 plus 173. So it's going to be like 500 something. 526.76, fantastic. In the y direction, we have 100. Actually, let's just deal with these first, because we have negative 5,000 plus negative 353 plus 100. So our normal force is going to have to be something like 5,253.55.
Yeah.
Mental math. It's brilliant.
I think it was just
Yeah, it was just a teacher. It's okay. So there we go.
Don't joke about the seizure.
But it amuses me. Don't make me put a strobe light in your face, Joel.
so what's the answer for y again?
I didn't even intend to, but I did. I'd use the patent colors of awesome. What was it in the y direction? It was like 5,253.55.
Yeah.
All right. This is the hardest equilibrium problem I could possibly throw at you. In this class, at least. Yes, Bree. Because if you can solve this, you can solve everything else. Well, then that's just a little bit of an issue, but did you get to at least, did you get partway there? Did you at least understand what was going on as we went through it? Well, it doesn't really matter what you call it. So that's okay. Like if, let's say you did this problem and the only thing you did was you labeled the applied force a tension force, I'm not going to be like, wow, you just don't understand any physics whatsoever. 15 points off. Okay, you'll be able to. Sure. Tell you what, I will write these out. I don't care. I mean, what's up, George?
Is the y direction supposed to be negative?
Down is negative. Up is positive.
But the answer for the y.
For the normal force, it should be positive because it's going up. Okay? Well, tell you what, I'll do that first real quick. let's plug in the numbers we had. Okay, so in the y direction, we had the y component of tension, which was 100, plus gravity, which was negative 5,000, plus the y component of the applied force, which was negative 353. That was negative. Plus the normal force all adds up to 0. Well, if you plug into your calculator 100 plus negative 5,000 plus negative 353.55, what you're going to get is negative 520, or 550, sorry.
No, it's 526.88.
What did you get back?
526.88.
Really?
No, I got 520.
I thought the problem was over.
It's all, it's in a matter of rounding. Be quiet.
I thought the
Your
problem
rounding
was
sucks. Alright, the problem is over, but I'm clarifying something. Alright, so you're going to get negative 523, or 5...
2, 5, 3.
There we go. 0.55.
Oh, that's for the other one.
So basically what you get is the normal force plus negative 5,253.55 must equal 0. That's why the normal force is negative. Because it must be equal and opposite.
I just dropped to go to force. I have to. Yeah.
Okay. Now really quick, the steps. Step 1.
It took up like half a page.
Are you at equilibrium? Step 2. Force diagram. Step 3. Break your vectors up into components. Step 4.
Can we have this on a test?
What?
Can we have this on a test?
Nope. But it's fine, because we have 3 more weeks of doing force problems. Trust me, these steps will be burned into your brain and you'll be muttering them in your sleep and everyone will think you're crazy. You'll be sitting in German class just muttering, step 3 components.
Oh my gosh, I'm getting my voice back.
You know what's more ridiculous is the fact that I can spell equilibrium with no problem, but until like I was a sophomore I couldn't spell brother. I kept spelling it bother, which may have been Freudian, but that's bother.
And you're a teacher?
Don't teach English for a very good reason. Okay, so there's the 5 steps for ethics contest. Alright, one more thing I want to do today.
Don't even say it.
Crap, I can't do it today, because we're running out of time. Alright, here's what we're going to do.
We're cooking hot dogs.
Tom, that's exact.
Wait, I had a quick question.
Yes.
Instead of hot dogs, you think we could
Whoa!
Hamburgers.
I'll put it back up here in a second, but I want to talk about one thing before we go tomorrow.
cookies?
No,
Brats.
shut up. Alright, so we've got to start talking about, starting tomorrow, we're going to talk about a slightly different version of equilibrium called ramp problems. So creatively named because they're problems involving a ramp. Okay? Now, if that block is just staying there, what forces must be present? Gravity?
Friction.
Friction which way?
Friction going backwards up the slope.
Up the ramp.
There's the force of the block going down the slope.
And then what else? There is no force of the block down the slope.
There's nothing.
Normal, which remember is perpendicular to the surface.
Oh, yeah, that's right.
Now, here's the trick. Done this way, how many forces do we have at angles?
2.
2. Friction and normal. Do you guys want to have to break down those 2 vectors and try and do all the trig or the geometry proofs needed to solve them every single time? Because I sure don't. Ramp problems are exactly the same, except there's a trick. Instead of looking at everything normally, we just kind of tilt everything a little bit. Instead of saying that xy is like this, we say it's like this.
Oh, geez.
So basically what we're trying to do
That's cool.
I'll get it.
is just tilt everything. so that now our ramp is nice and flat. So now what's the only thing we have that's at an angle? Gravity.
How long did it take you to figure that out?
What, the tilting thing?
Yeah, that's a cool little function.
I like it. And hey, anyone want to take a guess what this angle right here is going to be?
45 degrees.
30.
It's always going to be the same as the angle of the ramp.
You're gonna have to
This
tell me
is
that.
what we're going to get into tomorrow. Tomorrow we're going to do some example problems. We're going to do some more equilibrium. But right now, I've given you almost every equilibrium problem I've got. Okay. Now, your homework tonight
Just sleep.
is this worksheet. Now, this worksheet's not too bad. There are 2 blocks. All I need you to do is draw me a force diagram for block A. Draw me a force diagram for block B. And then over there on the left, there's that little line where it looks like you can put a letter. That's because that line, I want you to write, if you think A is pushing harder on B, you write the letter A. If you think B is pushing harder on A, you write the letter B. And if you think they're pushing the same amount on each other, you write the letter C. Now, something to be aware of on this worksheet. Look at that arrow above each of the problems. Do you see how sometimes it says constant velocity, sometimes it says constant acceleration? Not all of these are equilibrium. You don't have to do any numbers. Just know that at equilibrium, not all the forces equal out. Okay? Do your best on this. We're going to talk about this tomorrow. We're going to do some ramps. I'm going to break out some roller blades, and you guys are going to be pushing each other around. It should be entertaining.
That's tomorrow.
Okay?
That's tomorrow.
That's tomorrow. Yeah, look what you're missing, the Wizard of Oz people. Ha!